Swayam Prabha. Digital India. Educated India.
Hello. In the last two lectures, we discussed elastic pairs, that is narrow sections that connect two relatively rigid segments in a compliant mechanism, and felt that they can be modeled using empirical formula that many people have derived starting from 1965 when Paros and Weisbart did it, to even now people are trying to improve them and trying to find the ranges over which they are accurate and so forth. But instead of doing all that, today one can use finite element analysis and try to get the simulated response. But as we discussed, finite element is not so useful if you are trying to design. That is, you do not have a mechanism, now you would like to have one based on some specification, right. So, let us understand the difference between what finite element analysis can do and what it cannot do so easily. Okay. Today in this lecture we are going to discuss actually finite element analysis for modeling not elastic pairs, although we can do that also to have the small length flagship pivot or the circular notch hinge, all of those can be modeled using finite element analysis, but we will focus on elastic segments such as long beams or slender beams. So, we will have MATLAB code also run. So, we can see how we can analyze compliant mechanisms that have elastic segments. So, let us look at the slides and see that we have this parallel motion flexure mechanism that we had discussed in the last couple of lectures. So, once again we have these flexures over here. Let us get the ink. We have these flexures here, 4 joints, right. So, here if I apply a force in that direction, this block at the top is going to only translate. So, this one will translate. If I apply a force in this direction, it is going to translate in that direction, but there will also be a little bit of motion in the perpendicular direction, but no rotation. Okay. So, this one we can also do like this, it is a 2D one. So, I will just plot the 2D mechanism. So, we have the base, this is the base. So, instead of using this what we called elastic pairs, we have 4 of them in this, what we called elastic pairs. Instead of using them, now we will use elastic segments or beams, slender beams. They are slender because their length is much longer than their cross section dimensions, which we can just show like lines. I can show as thin lines. They both can be identical. So, let me just fill it. They can be strips of metal or plastic or whatever, and it could be single crystalline silicon as well. When you have such a thing, when we apply a force here, this is going to deform. Let us try to plot that. How does it deform? I said that it is going to only translate, there is no rotation. Let us assume that this has come down, it is kind of an exaggeration. It has come down and moved. Okay. So, there is some displacement in this direction and also there is some downward movement. That is what it will do. It will come down as it translates to the right, because these beams are going to deform like this. Of course, whatever I am drawing is exaggeration. We will do finite element analysis to see how exactly it's going to look, or if you have a real device, of course you can see. Okay. This is parallel motion because you have the original one and deformed here are parallel to each other, and this is used in many precision motion systems as we discussed in the last 2 lectures. Now, we want to analyze them. We can do that analytically. So, elastic pairs, when you do it, everywhere we will have these kinematic joints, and then we got equivalent torsional spring constant over here for all 4 of them, and then we have the rigid bars connecting them, and we can do kinematics and force equilibrium to see for a given force how it deforms. That is one way to do it. We will be doing that later on, but today we will try to do when we have these elastic segments rather than elastic pairs. So, how do you analyze this? We can also look at this folded flexure mechanism. Again, if you see, we had discussed this, when you have the top one, that is this one, we just saw that this block not only moves to the right when I apply a force over here, but also comes down a little bit, right. But if you do not want that, you want the stage, if I call this the moving stage, let us call it stage 1, we do not want that stage to move in the vertical direction. So, what has been done here is to add the second one, we have added the second one here attached to the first one. Okay. So, this becomes our stage 2. If you imagine here how stage 2 would deform, the stage 2 would deform, it will translate to the right, but at the same time it will move up. Just as this is stage 1 is going to move down, stage 2 is going to move up, and those two will be compensated. So, stage 2 will have pure translation in the x direction. That is the folded flexure mechanism. How do you analyze this? One of the things we should notice here is the ingenuity of this design. So, we are taking simply 4 or 8 flexures. Now, the way we did it here with 2 beams, if I add 2 more beams. So, I have the block here and I have beams over here, it is fixed and fixed. Now, this stage, what we can call stage 1, is going to translate in both x and y directions. So, we add another one here, another set of beams, a pair of beams. Now, attach this, the block. Now, this stage 2, if you dimension the beams, beam lengths and the positioning of the second block related to the first one, if you do it right as it is done here. So, they should all be aligned here, okay, which I have not done in what I have drawn. So, if we do that, this one is going to purely translate. Okay. Let us say we want to find that, we also find the stiffness. If I apply a force here, how much does it move? How much does this move? If it moves purely in the x direction, what will be this movement? Is, let us call it delta. We want to know what this delta is. If we know the geometry of the beams and their material properties, when I say geometry, the length as well as the cross section. Right now, we are taking uniform cross section beams. How do we do that? That becomes our strength of materials, as we incorrectly call, or mechanics of materials is what we will have. So, what we have is, if I say I have a beam which is fixed here, other side it has a block. Okay, I am looking at only one beam. So, what are we saying? This block is not going to rotate, and we are saying that if we do it right, we can also prevent its motion in the y direction, meaning, again let me say that this is y direction, this is x direction. That means that I can imagine that there are some rollers here. So, this block can move in this direction, but cannot move in the y direction also. Then how do I analyze this beam? Let us say this has a length L, Young's modulus E, and second moment of area I. If I have that, when I apply a force F here, how much does it deflect? And the deflection, as we have already seen, it is going to be like this. Okay, so the block which was there is going to move there. So we want to know this delta here. So it was over here, it has moved there now, we want to know what this delta is, right. So now if I just do the abstraction, if I have a cantilever beam that is guided here. So one end here it is fixed, the other end here is guided transversely, it can move this way. When I apply a force here, I want to know how much it moves, right. Some of you may remember these formulas right away as how much it will move, that delta you may remember something. If it is a cantilever beam, everybody knows, or most people would remember, it will be FL cube by 3 EI. So that 3 is for a cantilever beam, okay, but that is going to be different for fixed guided beam. Cantilever is fixed and free. That means that I will have this, if I have a beam like this and apply a force, it is going to deflect like this. There will be a slope here, whereas here the slope is 0, it is tangential to the vertical line, so guided. So what is this number? They all are going to have this form and there will be a number that is different, okay. That you can do by using what we call the summation, linear summation method, superposition method, where we take a cantilever beam plus which has this force F acting on it, another cantilever beam where there is moment acting, because when we are not allowing this to rotate, there is going to be movement, that everybody knows. So this problem that we have here, we are splitting into two of what we call static determinate cases. This statically indeterminate, we get this, and this can be done very quickly, you do not have to look up anything because this will be useful for analyzing compliant mechanisms. So let us look at what is known as this Myosotis method, which I have taken it from Dern-Hertog's book titled Strength of Materials or Mechanics of Materials. You need to remember only 3 numbers in this method. So this is 1 and then 2, then another 2, then 3, 6 and 8. So you have to remember 1, 2, 2, 3, 6, 8. And there are 3 cases here. Case 1, a cantilever with end moment, case 2, cantilever with a transverse force, and case 3 which has a uniform loading. In this case I think he uses the letter W, yeah, so let us use that. So there is W and there is P, there is moment M. So what is the end angle and end deflection? So all of them you can see the form ml by EI, and there is 1, ml square by 2 EI, PL square by 2 EI, PL cube by 3 EI, WL cube by 6 EI, WL to the 4 by 8 EI. So these numbers, if you remember, their form is easy to remember by just looking at the dimension of the quantity. This has no dimension, it is an angle. Deflection should have length units or length dimension, right. So if you remember 1, 2, 2, 3, 6, 8, then you can solve any beam problem for any boundary condition. So that is the Myosotis method. We can very quickly do this before we go to finite element analysis for this fixed guided beams. So what we are saying is that we have the cantilever beam with a force F here, and then we have the moment here and moment M, that is going to be equivalent to something that is going to only move like that, it cannot rotate, is what we want, fixed guided beam, right, that is what we have, fixed guided beam. So, let us get that condition. So, it is statically indeterminate. So, we do not know what this m is, but we can find the m based on the fact that if you do linear superposition, let us say the angle here, that is the rotation for this one and this one, theta at the free end due to f plus theta due to moment m should be equal to 0, because there is no rotation here, because we said that block does not rotate. So, what is theta f? If you go back and look at Myosotis formulae, so the rotation is this, is p here, we have f l square by 2 E I, that is the theta here. So, f l square by 2 E I, and then due to the moment, that is m l by E I, that is 1, that 1 here, right, m l by E I, that is the angle. So, we have m l by E I, that is equal to 0, which means that m is equal to minus f by 2. Okay, moment will be in the opposite to the direction that we assumed there. Okay. So, now I want to know the total delta over here. So, that is over there, how much does it move? So, delta f plus delta m will give me the delta that I want. What is delta f? You go back to Myosotis, and delta due to force is this, our familiar f l cube by 3 I. So, f l cube by 3 E I, and then we have due to moment, that is m l square by 2 E I. So, plus m l square by 2 E I, again 1 2 2 3 6 8 formula, noting that m is equal to minus f by 2, I can take f l cube by E I, that will be there for any beam by the way, and that will give me 1 by 3 here, and then m is minus half times f we have taken out. So, that will become half, and then 2 here, that will become minus 1 by 4, that will give me f l cube by 12 E I, 12 E I, right. So, in this particular case, the delta that we need turns out to be f l cube by 12 E I. Now, if we go back and look at our parallel motion flexure, we have one beam there that we analyzed, another beam. These two beams are in parallel arrangement. So, the force that we have here will be shared equally by these two, half half, force goes as half. In other words, when you have these two, the stiffness will be added because they are in parallel. So, the delta that we have here will be, we got f l cube by 12 E I. So, we have to add another of well, if I first get the stiffness constant f l cube by 12 E I. So, the spring constant for this will be f divided by delta, that will give me 12 E I by L cube, that will be the k for each beam. So, you have two beams in parallel. So, you have to add the spring constant, that becomes 12 E I by L cube plus another 12 E I L cube, we will get 24 E I by L cube. So, once you have that for a given force, you have the spring constant for the overall beam, you can get delta. This is how you can do by hand for small displacements. Now, let us go to finite meta analysis and try to analyze these things, because as things get complicated, for example, what we have done, if you go to this one, you have to have again 4 beams, each of which is fixed guided, fixed and guided. So, fixed guided relative to this one, this is fixed and this is guided, you need to keep on adding. Now, these two will be in series, and you can go like that, arrange identify the arrangement whether it is series or parallel, and you can get for any configuration of compliant mechanism. We have seen quite a complicated set of flagship mechanisms in the last 2 lectures. Okay. For doing that, we have to go to finite element analysis. Okay. Towards that, we will look at MATLAB codes and try to analyze this parallel motion flagship. So, let us look at the folder which has all the files to run finite element beam finite element codes in MATLAB. It has 4 data files: dispbc.dat, lm.dat, forces.dat, node.dat. We look at what kind of data these 4 data files have. You need to have the beam.m, that is m file, MATLAB script file, you need that, and then you also need FEM beam, and then you need 3 other files called matcut, plot beam lm, and then veccut. They are all MATLAB scripts, and there is also a readme.txt file that you can read about the format that these data files need to follow. That we will see when we get to the MATLAB code. We click on this beam, that is a main file that opens MATLAB. Sometimes version compatibilities may be there, you have to take care of few commands, but this is developed with the latest version MATLAB 2014. So, here you have the code which was written a long time ago, but it works and you can use it to run any type of 2-dimensional compliant mechanism. This font is little too large, so let us try to make it a little bit smaller. So, let us go to preferences and fonts, let us reduce it to let us say 18, so that you can see more of the thing. It did not do preferences 18, this is there, so I reduced it to 18. Let us say apply and say OK. It still does not. Okay, but anyway, bigger font is good, so you can see it. So, this one I already have loaded the input files. So, when I run it, when I run this here, run this, click this, it did it and it gave me the output file, where the dashed line here shows the parallel motion flexure before applying the force, and then after applying a force over here, it has deflected like this. Here we have 1, this is node number 1, node number 2, node number 3, node number 4, and there are elements connecting 1 and 4, and then 4 and 3, and then 3 and 2, the 3 elements, and we have taken care to make this one relatively rigid compared to these 2 segments. We have elastic segments, 2 vertical beams connected by horizontal block, that also in this code we have to model as a beam element, but we will make it rigid. How do we make it rigid? For that, let us look at the input files to see how we do it. In this particular case, when apply a force, it is deflecting the way it is shown. Okay. Let us look at the files here, data files. First one is node.dat, which has nodal coordinates. So, we have 6 nodes here. I talked about 3 in that plot. Let me tell you what these additional ones are. This is 1, 2, 3 and 4. Those are enough for this mechanism. Later we are going to add the folded beam. So, I have created 2 extra nodes. This is 1, 2, 3, 4, and then there is 5 here and then is 6 there. So, there are 2 extra elements, so that from there I can hang 2 other beams to make the folded beam later on. So, we have 6 nodes here. Those 6 nodal coordinates are shown here. The first one shows the node number, second column shows the x coordinate, third column shows the y coordinate. The first one is at the origin 0, 0, 0.5 and 0. So, the distance between the 2 vertical beams is 0.5 and the height of the beams or length of the beams is 1, the y coordinate, and then we have these intermediate ones 5 and 6 at 0.1 and then 0.4. Okay. Next thing that we need to look at, after defining the nodal coordinates, you can add as many nodes as you wish or as you need in a compliant mechanism. Now, let us look at the element, that is ELEM.dat. So, here we have 5 elements. Again, why are there 5 elements? Let us look at this code. So, this is the first element, flexible beam, second flexible beam is second element, and since we introduced 2 extra nodes here, I define this as a element 3, element 4, element 5. So, element 1 and element 2 are the elastic segments, 3, 4, 5 are rigid segments, and we will see how we make it rigid. So, the first one that connects 1 and 4, second one connects 2 and 3. So, this is the element number, first column, second column and third column indicate the node numbers that make up that element. So, node 1 is made with element 1 is made with node 1 and node 4. It has a rectangular cross section where the breadth of the beam is 5 centimeters, that is 5 10 power minus 2, and this is 1 centimeter breadth, this is B, this is depth D, and then Young's modulus we have taken steel 210 gigapascal, all in SI units, meter units. Second flexible segment is made up of nodes 2 and 3, second element 2, 3 and again 5 centimeters, 1 centimeter and then same Young's modulus. The other 3 elements, that is these 3 are supposed to be rigid. So, if you notice here the node numbers are 4, 5, 5, 6, 6, 3 and then they have 0.5 meters, right. So, this is 50 centimeters, this is 10 centimeters and same thing. This is how we can make rigid blocks in finite element analysis using beam elements. We make their cross sections much larger. If you want, you can make Young's modulus very large, whichever. What matters is E times I, Young's modulus times second moment of area. So, you can make either of them or even both of them very large compared to flexible segments. So, you can create a rigid block. With that, we are able to get the deformation like this. Where did we apply the force? We applied at this node, that is node number 4. So, we can look at the force file there. Again, this is the serial number, the force boundary condition, node number, and then I put 1 here. The reason there is 1 is that I am applying force in the x direction. In a beam finite element code, each node, when it is a planar beam, each node will have 3 degrees of freedom. The first one refers to x displacement, second one refers to y displacement, third one refers to rotation or the slope of the beam at that point. For beam finite elements, the slope degree of freedom and the transverse and axial or xy displacement translations, they are all independent. So, we have 1, 2, 3, 1 refers to x direction, and this is the force, some 1000 newtons I have applied, 1 into 10 power 3. So, that is a force file. We also need to say where we have fixed, that is contained in this file called dispbc.dat. Let us open it and see. We have serial number 1 to 6. So, we have 6 boundary conditions. What are those? This is the second column is the node number, third column is the degree of freedom number, fourth column is the value of the displacement that you have specified there. So, the first one refers to the serial number 1, boundary condition of the displacement, the first one is at node 1 and it is a x degree of freedom that is fixed to 0. If you want, you can also put non-zero values. And the second one, node 1 y displacement, third one node 1 the rotation, because if you look at our structure, this is node 1, this is node 2. So, these two are completely fixed, what we call cantilever condition. It cannot move in the x and y directions, it also cannot have any rotation, that is why it cannot have any rotation, that is why it is tangential to this line, and same thing here, right. And that is why we have node number 1 and then node number 2, all 3 degrees of freedom are fixed. With that, we are able to get the deformation that we got, right. But if you see if I zoom in here, how much ever I zoom in, you would find that there is no y displacement of this rigid block. It was here, it is still there. It has moved from here to here in the x direction, but not in the y direction. That is the nature of the linear finite element analysis. We have to run this with the nonlinear finite element code in order to see the more realistic one, because this structure in reality is going to have this block not only move in the x direction, but also move a little in the y direction, which is not shown by the linear analysis. One more thing before we go to nonlinear code that you need to notice is that from here to here I have a single beam element. So, in finite element analysis the unknowns are only the degrees of freedom at the nodes. So, I know the xy displacement and rotation at this point, I know xy displacement rotation at that point, right. So, if I join this point to that point after displacing them according to their values that I compute using finite element code, I would have a straight line from here to there, whereas here we have a curved line like this. That is because if we go back to our file, there is something called plot beam lm script that takes into account the slopes at this first node and second node and the displacement and interpolates using a cubic function, because for this beam element in finite element analysis we have used cubic shape functions, and that is what is used to interpolate in between. That is why we will get in the nice curve one that you see in the real device also. And this applies to any complex beam compliant mechanism that you make up, it will show you the interpolated beam also. So, you have degrees of freedom only at the ends, but you would know the deformation at every point. Normally in any finite element software this will not be, it will show as a straight line. If you want to see the curved one, then you have to put several nodes in between so that you can see the deflected profile, whereas if you use the shape functions to interpolate throughout the element you get a realistic picture. That is what we have done. Now, what we will do is we will go to nonlinear finite element analysis. I can open that here in the same folder that you are going to have. We are going to give you both linear and nonlinear analysis files. There is NL beam, it has a few more files, NL FEM beam and then plot beam LM, whatever we used in the linear analysis, and then we have matcut vector that you need. So, I will open this NL beam and try to run this. When I run this, it will say change folder, because that happens to be in a different folder. Now, you see we got a different one, because I have different set of input files here where I have applied some force. I have not only put this original one, but I also added the folded beam suspension, that is we have 2 more vertical beams hanging. Remember we had 5 and 6 nodes, now 7, 8 and there is a 9 also here. I will tell you why we have an extra node 9 here, that is what I have done. Okay. But then if I want to run the old ones on this, what I can do is, let us go back to the folder where we had these input files, which I will copy, 4 input files that I have. Okay. Let me copy these and then put them into the nonlinear folder. So, I am just copying, it asks copy and replace, we say yes for all 4 of them, because we want to overwrite what are there. Now, let me close these old ones, because they pertain to the linear one. Now, we are learning the nonlinear BM code, how to use it. So, now if I go there and run this, now you see it took the files that we used for linear analysis. So, it is only 6 nodes that we had, 1, 2, 3, 4, 5, 6. Now, you can tell whether it has moved down or not unless you zoom in. So, let us actually zoom in over here to see if there is any deflection in the downward direction. and you would see if I do more zoom in, there is indeed downward deflection also here because it is a nonlinear code, right. If I increase the force value, which we can, let us go to this force, open as text, now is only E3, node number 4 is what we applied. If I increase it, let us say that much, that is 10,000 newtons, let us save it, let us go to that nonlinear beam code, now run it. Now we can see clearly that it has not only moved in the x direction, the node that was here has moved all the way down here. There is movement in this direction and also in this direction. That is what the nature of the nonlinear code. Later on we will learn more about nonlinear finite element analysis, what it actually means, right. Now we have this. So if I have this one as the stage that is supposed to move purely in the x direction, I am not getting it here. When I do nonlinear analysis, which is actually realistic, it is moving down. In order to compensate for that, we add 2 extra beams, which is what we had originally when we opened the file. So let me go back and put those files and then see what happens. Again, instead of having this, I have 2 extra nodes, there is 1, 5 and 6. I am going to have a vertical beam and this. So in order to get a little bit of experience for that, let us actually try to modify it right here. So let me open these, so you get some experience of doing that. Note that that has 6 nodes. Now I have to add a few more nodes. So I am going to add 7, 8, 9 at the bottom, that is, let us look at the figure. So I have this original one, I am going to have 3 more nodes here, one here, one there, so that I can have this vertical beam and 2 rigid blocks. So the center I will have, that becomes a stage now, that becomes our moving stage, which is supposed to have purely x motion and no y motion, because we see that this top stage cannot have purely x motion, it has y motion, right. So if we do this, just as this is moving down relative to this line, the next stage that we hang, that is going to move up closer to its relative frame. So this downward motion, this upward motion, both are supposed to cancel. So you get this stage to move purely in the x direction. That was the intent of the folded beam suspension. So I am going to add 3 nodes here. So let us put that over here. So that is 7, and that I will put at 0.1, because that was node number 5, just below that, but I had to take it to 0th level, that is it comes down, that is 7, and then I will put 8, now node number 8. Node number 8 I will put at 0.4, because it should be right below node 6. So 0.4, that also comes to 0 there, and then I will introduce one more, which is node number 9, and this I am going to put in the midpoint between the two. So that becomes the center of gravity of the second stage, that is hanging from the first stage, that is also at 0th level. So I have 3 more nodes now. Let us save it, and then let us look at the element. So here already have 5 elements. Now I want to add 2 elastic segments and 2 rigid segments. So 2 elastic segments, again if you go back to the figure, I have to hang from that node to this node that I have created, and then that node to this node I have created. In between I have 2 more, that is from here to center of gravity to the other one of the element. So the 6th element will make it like a flexible beam element, that is going to be from node number 5 to 7 that we just created. So 5 to 7, and that is going to be flexible. So that is 5 e minus 2, 5 centimeter, and then 1 centimeter, and Young's modulus is 210 E9, and then 7th one also flexible, that is going to be from 6 and 8. 6 and 8, as you remember from nodal data, they are one below the other. Again that is 5 e minus 2 and then 1 e minus 2 and then 2 10 e 9. Okay. And then I also want to have these rigid elements that we have. So, already have 7 elements, I need to add a few more now, that is 2 rigid elements that we have, element 8 that I would do. The new nodes that we created are here. So, 1, 2, 3, 4, 5, 6, 7, 8, 9. So, 7 and 9, 9 and 8, that is what you need to have rigid elements. So, 7 and 9, and this is, I would like to put 50 centimeters, okay, half a meter, and this is also 1 e minus 1. We will keep the Young's modulus the same as before, and then one more element that is going to be from 9 to 8, node 9 to 8, and this is also a rigid one. So, 5 e minus 1, 1 e minus 1, and then 2 10 e 9. Okay. So, let us save this, and as far as the displacement boundary conditions go, they do not change. Still whatever were fixed, they are fixed, but forces we need to change, and force here, instead of node number 4, now we need to apply force for the second stage. If apply 4, let us run it, let us run the way it is now to see what happens. So, now you see it has deflected, this portion has simply moved like a rigid body, because if you see, now I have added these things, this and this are rigid, I have applied force still at the node 4 in the x direction. So, this has deformed, whereas the other one is like rigid block. To that one we attach a second stage with 2 elastic beams, that moves like rigid body because there is no force here. So, we have to apply really the force at this node, or we will at the apply the center of gravity, that is the node number 9. So, we will go back, go to the forces, this is the node number, second column, that I will make it 9. Let us save it, and now let us run it. Okay. You see that now we are applying force, it was here, it has moved a lot. Of course, let us reduce the magnitude and rerun it, but what you notice here is that this is stage was over there, it has come down, whereas this one is at the same level. We can actually zoom in and find out if there is any deformation at all. If you see, it is exactly at 0 0, how much ever I do. If you want to see the line, we can come and type grid command in MATLAB, that will create a grid in the thing. You will see that it is right on the little bit difference is there. See, now I have really zoomed in a lot. This little deformation, this difference is coming because it is nonlinear code first of all, and other is that these beam elements and are elastic segments, whereas this is rigid segment. I just made cross section 10 times larger, but they may also be deforming a little bit. Another reason is that when you look at the spacing between the first stage elastic segment, that is from here to here, that is 40 centimeters, sorry, here to here, that was 50 centimeters, whereas this is from here to here, that is less than that, it is much less. So, it goes to 0.1 here, 0.1 there, about 30 centimeters, right. That also matters for how much it would move in this direction. That is, if I were to take these beams, put farther apart, how much it comes down actually is affected by that spacing. You have to do nonlinear analysis to find out how much that is, and that is why if I really zoom in a lot, then I start seeing the change. Okay. If you want to make another modification, which we will discuss after reducing the force. So, it will be, let us not apply so much force, let me apply 1/10 of that, only 1000 newtons, and then go back here and run it. Now, it is little bit better. No, what was the stage here has moved over there. Again, if I zoom in, I might find that it has deflected a little bit. I am really zooming in a lot, then I see that there is a little change, okay, over here. several levels I had to zoom in to see that. So, otherwise there is not that much of this. If I really want to avoid this also, then as you remember from the earlier part of the lecture, where the first stage and second stage are connected with a lever. Again with a couple of lectures we can do with beams here. The reason that lever is needed is for this spacing, the original spacing from here to here, there will be a little bit of downward deflection. From here to here for the second stage there will be a different amount of deflection. So, if you know those deflection ahead of time, you couple them using the corresponding lever ratios. There were letters A and B. If you arrange them correctly, you can make sure that even under large displacement, this particular stage will not have any vertical motion. Okay. So, now we have a stage where applying force, it moves like this, right. So, once you have the code, you can play with it. Let us do that now. Instead of applying force in the x direction, let us see what happens if I apply in the y direction. Let us save it and now let me run it. You see hardly anything, because when I apply a force in the vertical direction, this will be very stiff. That you can imagine that if you have a beam, transversely it will be flexible, but axially it will be very stiff. So, for the force that we have applied, which was 1000 newtons, it is hardly moving. And we can see the values also. In MATLAB, when you type WHO, we can see all the variables that are there. Okay. That u is the displacements. Okay. If you type u, it will show you all the values. Of course, there are a lot of values, it just shows that. What we need is the displacement, let us say at this node 9, which was in the middle, how much is it moving in the y direction. So, the node 9, the degrees of freedom of that are going to be coming from back 27, because each node has 3 degrees of freedom. If you have 9 nodes, there will be 27 degrees of freedom. Those 3 degrees pertaining to node 9 are going to be 25, 26, 27. 25 in the x direction, 26 in the y direction, 27 the rotation. So, if I want to look at what is the y displacement, I have to look at degree of freedom 26, u 26. If I do, it will show this is about 10 micron, 9.69 microns for a beam that is 1 meter long that we have taken, and properties geometry you have, you can go back and check. It moves very little, very stiff, right. Now, for fun, let us actually apply a moment load there. I make it 3 degree of freedom. Let us save it. Let us look at it now. Still nothing, not much. Okay. So, if I have to do this, I have to apply very large value. I will put 6,000 times more, that is 1 mega Newton meter. Let us see what happens if I do. Okay. Now, you see it is rotating, that is I have taken this and rotated. When I rotate it, you would have expected that this stage will simply rotate, but it does not. It actually moves from there to here. That is the rotation of the stage, the second stage, we are talking about this stage now. I applied a movement at this point about z axis out of plane, right. When I do that, it not only rotated, but also has moved. That is called the cross axis influence. That is, you are asking it to move in a particular applying force there, but the stages that you have, these compliant stages, will not do that. They also will try to move in the other directions. That is the difference between rigid body mechanisms and compliant mechanisms. Compliant mechanisms, since they can move in other degrees of freedom, they do. So, they have this rotation also. Now, if you remember in the first lecture and an earlier lecture, we talked about a stiffness matrix that we can construct for this block, or for that matter any part of compliant mechanism at any point. Now, let us say the second stage block, I would like to know its stiffness in the x direction, y direction, and then theta direction, as well as the cross axis, meaning when I apply rotation about z axis over here, it has led to axial x displacement and y displacement. So, for that I need to construct a 3 by 3 matrix. Let me first go to PowerPoint, actually show you what I mean. So, let me just draw that. So, I have at that block. So, now we have that beam, and this top block is there, and another beam, and this is fixed here. That is the parallel motion stage. Now, we have two more things added, and we have this block here. Now, what I am saying is that what we just ran is applying a moment load on it. When we did that, instead of purely rotating, it also moved in the x and y. Why does it do? Because the 3 degrees of freedom of this one, if I call this ux, uy, x displacement, y displacement, and theta z, okay, and these will have corresponding forces fx, fy, and moment mz that we just applied. Of course, these two are not equal. There is a stiffness matrix. Okay, this is 3 by 1, this is 3 by 1, this is going to be 3 by 3. So, we need to get these numbers here. So, we need to get these numbers here. It is going to be symmetric matrix, we need to get those. The way we want to do this is what we call stiffness matrix. Stiffness matrix, which basically models all of this, effect of all of this on this block, so that we can have this block as if it is connected to two springs like this. That is, entire mechanism we are modeling with these springs, and there is a torsion spring also here, right. But this is not complete because we do not talk about this cross element, right, that is not here. So, having this kxx, if I call it kyy, that is this going to be kxx, this is going to be kyy, and this will be k theta theta, right, this torsion spring constant. That is not enough. There are these 3 more things also we need to get. We can get that using finite element analysis code, which is what we will do now. The way we will do it is to construct what we call the compliance matrix, which is inverse of this, meaning what this will do is it will try to relate the inverse of the stiffness matrix. Now, this is stiffness matrix, this one is called compliance matrix. So, this will relate fx here, fy here, and mz, and then these will be ux, uy, and theta z, and this also is a 3 by 3 matrix, and this we denote by C, we denote this by K. This is the K matrix, this is the C matrix. In order to get this C matrix, what we will do is we will apply unit force one at a time. We will apply Fx equal to 1. When I do that, at that point in the finite element model, I will have x displacement, y displacement, and theta z, right. So, if I apply unit force in the x direction, I will get displacement in the x direction ux, I will put that there. So, I will put the displacement I get when I apply force only in the f direction over there, and the y direction displacement I put there, whatever slope I get I put here. When I do that, you see, when I apply force only in the x direction, when I multiply this row with this, I will get ux, because Fi and mz then are 0, I get this value over there. For that I will get this value, and when I apply this, what I need here, when I want to get uy, I take the second row and multiply this. When I do that, this is a symmetric matrix, that is, this value will be same as this value, this multiplied by that will give me ux. Okay. So, I need to do 3 finite element analysis runs in a 2D case, apply force as 1 Newton there and other things are 0, and then another analysis where I apply this 1, other to 0 and apply 1 Newton meter here, other to 0, 3 finite element analysis, which is what we will try to do now. Going back to MATLAB. Okay. So, we can go back here and go to forces, other node 1 I will apply in the x direction. So, 1 Newton, save that and go to NL beam and run it. Okay. You hardly see anything, 1 is too little for it, but then we have all this displacement that we know about, right. So, if I look at U25, that will give me the displacement whatever 9.5313 10 power minus 5, right. If I put this as the first entry 1 entry of the C matrix, I get that, and then I look at the U26, which is the y displacement of node 9, this 5.2712 10 power minus 12, I put that as second one and third one. For the U27, if I take, that will give me 1.411 10 power minus 7. So, I put that, I get the first row. Then I go back here and change it to 2, save it and come back and run another finite element analysis run. Then I get again changed the displacements. I look at degrees of freedom correspond to this node 9 that I am interested, I get the second row and then apply moment here, changing this to 3, I get that. If I do all that, I will get something that we have the C matrix. Okay. You take the inverse of that, then you will get the stiffness matrix. That stiffness matrix will give you, as we saw, this stiffness matrix that let us actually go here. The stiffness matrix, first you consider C matrix by putting these things, you take inverse of that, you get this matrix, which you can actually verify with analytical formula that we did earlier in the lecture, which would give you whatever that value is you compared. Okay. And you will see the difference between linear and nonlinear FEA. So, if I do the linear and nonlinear FEA, there will be difference. For example, with the same data files that we now have, we have the nonlinear files which we have changed, right. So, if I put the linear one, you will see the difference. So, we have that and this. I will copy these, put them into the linear finite element code, overwrite all 4. Now, go back to MATLAB and I will close these files, go to beam, now run it, change folder. So, now if you see we get something, but let us actually look at the force data where we are applying force by putting a large force here. This in node 9, I will apply in the x direction. Let us put this E4 that we had earlier, or E3, that is 1000 newtons. Come here and run. Now, you see that this one, if you go here and zoom in, there will not be any vertical displacements, right. How much ever you zoom in, you do not find anything, because linear one cannot do that. So, here also first stage also it is not, that we had already seen, that is what you get. But what we learnt now is, if you have finite element analysis code with you, you can generate the lumped stiffness matrix for any rigid segment that you have, or even a point. At that point, how does it feel in x, y and z directions. So, you get the cross axis stiffnesses also as part of this, or you have to do 3 finite element analysis in 2D and 6, because in 3D, because in 3D you have 3 translations and 3 rotations, all of that you can get. Now, one more thing I would like to show before we leave this is I also have over here lot of other data file, the 4 data files, some crimping mechanism and a gripper and other things. So, let us actually go to this gripper, and we have these 4 input files which have many elements, and they are already pre-done. So, now let me put those files over here into this folder, copy and replace. Now, if I go to MATLAB and try to run it, okay, we got a gripper one done. So, let me enlarge it a little bit, and that mechanism I have with me. So, you can look at this. So, this is the mechanism that we have simulated there. In this one, when I apply force over here like this is closing in, this is like a gripper. So, this is a symmetric mechanism. Whenever there is symmetry, we do not have to model completely, we will model only the top half. So, if I cover this, whatever is there is what we have the code in the MATLAB that we just ran. So, there we have to apply force down here, and then if I apply both, if I take half, if I fix it, if I do this, this will close in as it is seen in the MATLAB simulation. So, it is a symmetric mechanism. So, we are taking only the top half for analysis. That is something to remember. When you have a symmetry in a device, you take one half, and that is good enough because you save time computationally. And with this one here, we have again lot of beam segments, one here, second, third, fourth, we are applying a force there and it is moving down. So, we can just put in the data files and get this. There is another one over here. So, there is something called a crimper that has also 4 input files. So, for all of these mechanisms that we have a collection, so for all of them we have these files which you can use, and if you have a new mechanism you can put them all here. Now, I go back to MATLAB and run this, that shows a different mechanism. So, that also I have here. So, which has a thing like this, when I apply a force, you can see the MATLAB deformation that we had. When I apply a force, it moves, this portion is moving up, right. So, you can ever so little, it is a force amplifier. Put your finger here and then do this, you will feel the amplified force. That is why it is displacing a lot at the input and moving a little bit at the output. So, this one, even though it is symmetric, we have modeled the whole mechanism. So, over here we have taken the entire mechanism, applied forces here and here, how it moves. It has moved a little bit, as you can see, it has moved from here to there. So, let us say for this block, if I want to get the 3 by 3 stiffness matrix, then I have to run this finite element analysis 3 times for this by applying force in the x direction, y direction and the slope, and get the equivalent stiffness of that block by hiding the details of the rest of them. Then I do not apply input force here, I have to apply on the block itself. It is supposed to be a rigid block. On that block I need to apply x direction force, y direction force and rotation. And the same set of files that I have, I can also copy them into our nonlinear code. There is a different folder. Let us put them there, copy and replace, and then now run the nonlinear code, change folder. Now, it shows, but here you can't tell the difference much because this is moving a lot, but this is nonlinear code, that was the linear code, but this will be more realistic. Okay. And how much value this would have been versus what was there for the linear code, there will be differences, and we will discuss that in a different lecture as to what is the essential difference between linear and nonlinear codes. Okay. So, now we have spent a lot of time to familiarize with the MATLAB codes, both linear and nonlinear. The theory for this, you have to take a finite element analysis class for that. Otherwise, we are going to put some supplementary files for you to look at, where the theory of finite element analysis for these codes is explained in a few PDF files that you can download and read. So, what we have learned now is that any compliant mechanism, how much ever complex it is, as long as it is in 2D and it has beam segments, we can analyze it, we can also find the equivalent stiffness for a rigid block that may be there on it. Thank you.